All right, we are at section 2.6, motion diagrams. This should be I think, a fairly short section. It's only 3 slides. Velocity and acceleration are often confused with each other, but they're different quantities. A motion diagram is useful in forming mental representation of the moving object. It describes the velocity and acceleration while the object is in motion. So to get a motion diagram, imagine a stroboscopic photograph of a moving object. It shows several images of the object taken as a strobe light flashes at a constant rate. The figures show that the time intervals between flashes of stroboscope are equal in each part of the diagram. The red arrows indicate the velocity. The purple arrows indicate the acceleration. Um, so if we look at figure, the top image A, the images of the car are equally spaced. The car moves through the same displacement in each time interval. The car moves with constant positive velocity and zero acceleration. So the red arrows, the red vectors of its velocity are all equal, and there's no purple arrows. They're because acceleration is zero. If it's constant velocity, the acceleration is zero. The particle under constant velocity model, the red velocity arrows are all of equal length and no purple acceleration arrows. Their length is zero. There is no acceleration. Now, figure B, the middle figure, images become further apart as time progresses. And remember, these are equal intervals of time. The red velocity arrows increase in length with time because the car's displacement between adjacent position increases in time. In other words, it's going faster with each increment. The car is moving with positive acceleration and positive velocity and positive acceleration. The velocity and acceleration are in the same direction. Imagine a force pushing or pulling on the car in the same direction as it is moving, so it speeds up. Now, figure C, the car slows down as it moves to the right because displacement between the adjacent images decreases with time. The car moves to the right with negative acceleration. Lengths of the velocity arrows decrease in time and eventually reach zero. The acceleration and velocity arrows are not in the same direction. The car moving with positive velocity but with negative acceleration. Example, a car that skids to a stop after its brakes are applied. The velocity and acceleration are in opposite direction. Imagine a force pulling on the car opposite to the direction that it is moving. It slows down. Each purple acceleration arrow is the same length. That is, the particle is under constant acceleration. That's what the purple arrows of the same length indicates. Time for a quick quiz. Which of the following statements is true? If a car is traveling eastward, its acceleration must be eastward. If a car is slowing down, its acceleration must be negative. Or C, a particle with constant acceleration can never stop and stay stopped. Which of those is true? Well, it's C. The particle with constant acceleration can never stop and stay stopped. Think of we haven't gotten to gravitational acceleration, but a ball that you throw up in the air is under gravitational acceleration. If you throw it up in the air, it will come to a stop, but it won't stay stopped. It'll eventually change. So a particle with constant acceleration can never stop and stay stopped. It's going to change velocity. Okay. Okay, this ends our discussion of motion diagrams. The next section we'll discuss will be analysis model particles under constant acceleration. We did a analysis model of particles constant velocity. Now we're going to do it under constant acceleration. Okay.